This talk is about a gaze into the internal logic of graph neural networks with a bit of logic programming, but specifically Prolog. And let me start by overviewing it. The main objective is to model with help of a logic program what happens in terms of information flows that are needed when a graph neural network is learning properties of new node, properties that it has not seen before. The inference process distills information from the link structure of the graph and also the information content of its nodes that could be text or image or something really specific and which is unrelated to the connections to its neighbors or faraway peers in the graph. So one of the algorithms that graph neural networks use is based on information exchange between nodes using message passing. And we would like to see a little bit of the details of that and how close we can get by just doing it via the equivalent of message passing in terms of interactions between logic components, predicates. But besides that, we'll also infer upper bounds on what can be learned from the graph's link structure on one hand, and the content of its labeled nodes on the other hand. So we have even a practical outcome. We obtain a logic program that, if seen as a machine learning algorithm, performs close to the state of the art on a reasonably challenging node property prediction benchmark. So we are committed, of course, to replicable results, and the code on which this paper is based is available at the link below here. Okay, let's get to the next page. So we pick a data set. This is an application paper, and it's a citation network from arXiv, and it's part of the Open Graph benchmark set, which is used quite heavily for benchmarking several algorithms in graph neural networks. So the original OGB graph has the following structure. We have a node identifier, an embedding of the abstract of the paper, that's a vector, and optionally, but we fetch it actually, the summary itself of the paper. That would be the content element, and of course the links between papers, the reference links, would be the graph structure. Of course, we have a marker that says if it's in the training set, in the validation set, and the test set, and also a label indicating one of the 40 arXiv computer science classes from 0 to 39. So that's what we need to predict for a paper, to which class it belongs based on its citations as well as its content. The summary's content, that's all we have here. In terms of Prolog, we have a directed acyclic graph derived by merging the dependency trees of each sentence of the summary associated to each node. So the dependency trees will extract them using the Stanford dependency parser. A list of each node's neighbors containing the node identifiers of the cited papers associated to a node. And the data set, as converted to Prolog, is available at this link here. So let me show you a little bit how this dependency directed acyclic graphs look actually. They come from the dependency trees. I put here a sentence about logic programming and functional programming they're both declarative, and we compare a bit how they evaluate and what are their common features, specifically in this case unification, which is used for evaluation in logic programming and for type inference in functional programming. So after you do the dependency trees for each of those sentences, and then you kind of merge them together in a dependency graph that's not cleaned up. There are some moderately low semantic information words here, like as or for, or well, and has its merits, but some of those verbs here, like be here, are not as important as what they actually connect. So the next thing done here is to actually clean up a little bit that graph. And how we do it? Well, the easiest way to do that is to run PageRank on the reverse graph, because we want what's more important to be closer to the text root, right? The verbs and the nouns. So we revert the links in the graph, and then with PageRank, we eliminate the low-ranked nodes, which are usually noise words or whatever else is there that's not particularly important in the corresponding paragraph, or in more general case, a text document that could be as big as we wanted. This is a relatively quick algorithm. So that's what we call the distilled dependency graph of the paragraph. Now, the label inference algorithm, this is the key of what we do to emulate what graph neural networks do via message passing. We analyze the labels of a paper's references when we know them. When this information is not available, we use content similarity. And for that, we have to invent a few nice ones. So we'll show them in a minute. And then, of course, we want a voting mechanism. We would like to prioritize the most relevant and also possibly content-wise close neighbors with known labels. Usually when you have papers that refer to other papers, that comes from the future to the past with a few present to present links, which we don't want. The training set is clearly separated here by being older than the validation and the test set. So how we do with our little Prolog code here, we have some parameters that limit a bit how far we go in terms of how many neighbors we look at, and a bit of an influence of the most frequent class, which is a good heuristic. Frequent classes are more likely to be good default values if you cannot find a neighbor that's relevant. And then we will look at the neighboring data. Those are the one-step close peers. And then we look at peer data in general that could be as far as we want, but semantically related. And then finally, we have a voting algorithm that combines all those things. So the predicate that does the voting, that's called vote for the best label, implements this weighted voting mechanism. And what we do, we just sum up the weight of each label that is of the same kind. I mean, the same CS label as archive marks them, and it picks the one with the highest total weight using the predicate max member that's a built-in in SWI. So that's a little bit of nice Prolog short code that groups pairs by keys, and then we have a summing up mechanism for the vote. So Prolog is reasonably expressive and convenient for expressing all that. So a comment here is that the vote for best label can be seen as an approximation of the message passing information propagation that graph neural networks use, giving the peers of a node a say on the node's decision to pick a given label. So we try to learn from our neighbors in the past that are kind of similar, what's their class, CS class in archive, and try to inherit from it as well as possible and as nicely weighted as possible. So by using the distilled dependency graph, the directed acyclic graph, which, by the way, matches one-to-one to ground Prolog terms. That's what Prolog terms are, the ground ones in this case. We introduce a few similarity measures. So some of them have their maybe merit on their own to be used elsewhere when we want something weaker than exact unification, to just see how close facts might be to a query that wants to retrieve them. One of them is the shared path similarity. It extracts segments of path in the trees corresponding to two terms, assuming that the order of the arguments is irrelevant, and that distinct functor symbols at the same level can be skipped. So Prolog has arguments, but we want in this case to ignore the order because we cannot exactly predict in which order the dependency links would be below a head term. Another one is termlet similarity. We sum up the sizes of subterms up to a given size, and we count them. And then finally, a very simple one, but quite effective actually, after those dependency trees have cleaned up, focused on what's important, then the Jacquard similarity is simply the size of intersection versus the size of the union on a set of constant symbols occurring in the DAG. So all the leaves that you have seen in that DAG, seen as a set, and then we divide the intersection, the size of the intersection with the size of the union. So with that, we actually get a few accuracy measures. So we do some benchmarking to see how close we can get to the state of the art, which is computed by the best graph neural networks. So for that, we run our label assignment algorithm for several similarity relations. We do not use the embeddings, as our objective is to evaluate our symbolic algorithms. The embedding would be the vectors that are associated, that come with the data set, 128 long vectors generated by something like word2vec. They are very good with something like cosinus similarity, which in a way represents closeness. And that closeness is a distributional property. It's learned actually from how those words behave in very large data set of text documents, and the ones that kind of co-occur and are close enough in terms of their usage will have hopefully better similarity. But our symbolic similarity relations are not very bad. What we have here is that when we have some weird similarities. One is the mock similarity, which says everyone is similar to everyone. This brings democracy, actually. When you compare without caring how semantically similar two nodes are, well, then it's as many nodes as you have there, and they all have one vote. So that's a democratically weighted voting mechanism. And we have the termlet similarity, the shared path. We have a variant of that I didn't mention, which uses forests, actually. And then the Jacquard similarity for either edges or nodes, intersections and overlaps. And what we get here in terms of performance, the best one would be this one here with the Jacquard node similarity is 68 accuracy, 0.68 accuracy. So 68 times in 100, we are guessing one of the 40 labels, which is reasonably non-trivial because there are 40 choices there, and we hit 68 out of 100 by doing no machine learning, just purely symbolically. The performance impact of the graph structure versus similarity-based node content is then expressed here, the line below, is when you ignore completely the graph structure and you just go with symbolic similarities, and that's not necessarily good. The mock one, of course, is not great. The termlet similarity is so and so, and the Jacquard similarity wins here by a good margin, which also, of course, explains why it performs the best with keeping also the graph structure in our mind. Now, what's the state of the art here? Well, the state of the art is higher. The baseline that comes with the OGB default graph neural network is 0.72, so 4 points higher than our symbolic algorithm, but they have a leaderboard, and on the leaderboard, the current value is 0.74. So we are reasonably close, but of course we do not have the fully differentiable learning mechanism that fine-tunes all those weights and propagates information more than one neighbor away and so on. So that's our performance here. So now a few comments on the importance of the graph structure node content and an element that's called diversity here. Diversity is a good thing most of the time. So the results that we have here show that when we hide the connectivity information of the graph and use exclusively node content similarity, our best result is pretty low. When bringing in 40 rather than the default content pairs, which the algorithm has a parameter that can control, the resulting accuracy goes up at 46, which says that by just bringing in enough diverse pairs, that increases the effectiveness of the node content similarity measures. When using also graph structure, that can be lifted to as big as 0.6930. That's running a bit longer because we compare with so many peers, but after that you have diminishing returns. So that brings us 3 points below the OGB GNN result, which is where this approach basically maxes out. So we detect a few limits here. One of them is related to how much you can learn from the graph structure, and the other is how much you can learn exclusively by using node content. Here we get an upper limit, and it's clearly almost a statement that even a graph neural network cannot go above that. And here we have an interesting paradox in which the node content, if a perfect mind would look at all the nodes, will then go as high as possible, because the most similar nodes in a human sense would be enough to improve the relatedness performance. But the pragmatic limit seems to be this one based on similarities. So my conclusions here, the declarative simplicity of our code shows the effectiveness of a mature Prolog ecosystem as a competitive exploration tool, revealing fine points about the internal logic of deep learning tools. We focused here on a concrete data set, but the methodology is generalizable to other graph-based datasets and also link or graph property prediction tasks. While we have observed that the graph structure dominates, we have also discovered that it is possible to use faraway peer nodes that can bring diversity and ensure better performance in a very similar way as some of the graph neural networks learn long distance dependencies and gleaning information from faraway neighbors. So overall, we get an actionable hint on designing graph neural networks that are able to reach far away in the graph's link structure, guided by content similarity measures. Thank you very much.